Hello students, welcome back. So we talked about the module instantiation technique in the previous video, and now we are going to implement a full adder using the same technique. So in this video we are going to talk about that what is the functioning of a full adder, what is the logic diagram of a full adder, and how can we implement a full adder using two half adders. And we are going to do that using the module instantiation technique. So let us get started. So full adder is different from half adder, and how? So let us first discuss that. We are saying that the completeness of addition operation is done using full adder. In the half adder, we were adding two numbers A and B. We were generating one bit of sum and one bit of carry. Where does that carry go? The carry of one significant bit or the stage will go to the next higher stage. So that will act as the input carry. So basically we have to add numbers A and B with the input carry. So we are going to take the input carry along with two standard inputs, and effectively three numbers will be added. So that is the process of full addition. When we add three numbers whose values are either 0 or 1, so the minimum sum can be 0 and the maximum number that can be generated is 3. To represent any number between 0 to 3, we need 2 bits. So the output is going to be 2 bit. One of them will be called sum and one of them will be carry. Let us understand full adder with the help of a truth table. So here we have three inputs A, B and C in, and we have two outputs C out and sum. When we add the 3 bits of our input, we get the output. Let us check the case number 1. If I add 0 with 0 with 0, the answer is 0. So I have represented 0 in 2 bits, that is 0 0. When I add 0 with 1, the answer is 1 and it is represented as 0 1. Let us take the example of 0 plus 1 plus 1. So the answer should be 2 and 2 is written as 1 0. If I take 1 plus 0 plus 1, then also I get 2. If I get 1 plus 1 plus 0, then also I get 2. And if I take 1 plus 1 plus 1, then I get 3 and 3 is written as 1 1. So here I have 2 bits of output, one is sum and one is C out. Now I need to find that what is the logic diagram or the Boolean expression that relates sum in terms of ABCE and C out in terms of ABC in. So when we solve this truth table, we get the logic diagram and the Boolean expressions. The expression for C out is A and B, or with C in A XOR B, and sum is A XOR B XOR C, and according to these relations we got this logic diagram also. How did we obtain these expressions from the truth table? We'll talk about these techniques more in detail in our next module, which is about the combinational circuits. So right now we are assuming that we got this logic diagram. Now when we look at this diagram in detail and we find that one XOR gate and one AND gate, they are having same input A and B, both of them, and XOR gate output is S1 and AND gate output is S2. Well, this is same as half adder. In the half adder also we had one XOR gate and one AND gate, and both of them had same inputs A and B. And interestingly, we are able to locate one more half adder in the same circuit where the inputs are S1 and C in. S1 and C in are the input for the XOR gate as well as AND gate, and then there is one OR gate. So we can say that one full adder is made up of two half adders and one OR gate. So therefore, we can use the module instantiation technique in implementing a full adder using half adders. So students, now we have the good idea about the design. In the next video, we are going to use Verilog and implement this full adder using half adder and the module instantiation technique. Keep learning. Thank you.